All right, good morning, everybody. So to remind you where we left off in the last lecture, we were talking about implementing lists in Java. And so we had the beginnings of an array-based list implementation. It's also generic. Our class sArrayList of some element type E implements this simplified list interface that we had in the previous class. It's a generic collection that's an array-based collection, so we have an array of object rather than an array of type E. So remember, in Java, you're not allowed to make an array of type E, so you can't make generic arrays in Java, so we have to make an array of object here. The usual constructor, the usual size method. Right? Here we have the add method. So add is exactly the same as push for an array-based stack. Right? So there's nothing special here. So the thing to notice here is that line right there. Right? So when you add to the end of an array-based list, or any array-based collection, if the array is already full when you perform the add operation, you have to resize the array. Right? And resizing the array means copying the array, which is an ON operation. So in the worst case, adding to the end of an array-based list takes ON, has complexity in big O of n. Right? Now notice this you only need to resize when the array becomes full. So most of the time when you're adding to the end of the list, you don't have to resize, in which case all you need to do is go set an element in the array, which is in O1 time. So on average, it turns out that adding to the end of an array-based list or any other array-based collection is in O1. Right? Okay, here's the get method. So get gets an element from the list at that index. Right? Check index simply looks at the value of index. So that's an O1 operation. Returning or getting the value from the array is again an O1 operation, right? We just need to look at whatever element is in the array at that index and then return it. So get is always in O1 for an array-based list. Set is similar, always in O1 for an array-based list. Adding somewhere into the middle of the list or perhaps at the front of the list has worst case complexity big O of n. Right? And so on that line there, so I've remarked this slide because to indicate where the error is. Right? So on that line right there, you might have to resize the array when you add to it. Right? Regardless if you add to the end or at the beginning, it doesn't matter. Right? If the array is full, you have to resize the array. So that's an ON operation. So immediately we know in the worst case it's ON. And then there's another loop sitting here. Right? And that loop, if the index is 0, runs n times. Because you have to move the elements to one position to the right, right? So move all existing elements from the insertion index onwards, one position to the right. So that, again, is another ON operation. Right? So adding to the front or into the middle of an array-based list has complexity big O of n. Right? And remove is similar. So removing, you have to move the elements from the index past where you're removing from, one position to the left. Right? If you remove the front the front element of the list, you have to move all the elements of the list one position forward. Well, all the remaining elements one position forward in the array. Right? So again, that's another ON operation. Right? So if you're using a list for some computational problem, right, and you need to frequently remove from the front or frequently insert at the front of the list, you probably want to reconsider using an array-based list. Right? Those operations are in ON. Whereas the other list-based operations, most of those are in O1. Okay. All right, so we actually stopped at this slide here. And so when you're implementing a list, you probably want to let people iterate over the elements of the list. And so that means you need to provide an iterator for them. Right? In our list implementation, our interface says the interface extends the iterable interface. And so that means all our lists must also implement the iterable interface. So we have to provide an iterator method. And if we provide an iterator method, we need an iterator. Right? And so we're going to have a private class called ArrayIterator that actually implements the iterator for our array-based list. Right? So just to quickly remind you exactly what the iterator interface does. Well, I guess I should remind you what an iterator does. So an iterator is just an object that knows how to iterate over a sequence of values. So it turns out that for lists, it's quite important to provide an iterator. using an iterator is the only guaranteed safe way of iterating over a list or set and removing elements during the iteration. So this, this operation here is called filtering. Right? You'd like to, when someone says they want to filter a list, it means they want to look at the elements in the list and remove certain elements that meet a criteria. Here we go. So I'll show you how to do that in just a second. Right. Whenever you write a for each loop in Java, you're actually using an iterator object. Right? The language is hiding the creation of the object from you, but that's actually what's happening. Right? And so when we implemented iterator before, I told you every iterator has two methods. Right? It has a hasNext method and it has a next method. Right? So next returns the element that the iterator is currently pointing at or visiting. Right? And then it moves the iterator to the next element. Right? hasNext returns true if there is more elements to look at in the collection, right? And it returns false if not. Right? There's also a remove method. Right? And in the iterator interface, it's marked as a default method, right? And it throws an exception. Right? And so this is Java's way of indicating that the remove operation is an optional method in an interface. Right? So if you don't want to provide a remove method for your iterator, you don't. Right? And you end up with this implementation here. Right? If someone tries to remove something using your iterator, they get an exception, which is fine. Right? Now, if you want to provide a remove method, then you have to override the default implementation. There is another default method here. It's not relevant for our purposes. So what remove does is that it removes the element that was most recently returned by next. Right? So remember, so the way you use these iterators is you call next to get the, you create the iterator, and then you call next to get the first element. Right? If you call it again, you get the second element. If you call it again, you get the third element, and so on and so on and so forth. Right? If you call next, you're allowed to call remove. Right? So every time you call next, you're allowed to call remove once. Right? So remove removes the element that was previously returned by next. If you call next and then call remove twice, you get an exception. Right? You get an illegal state exception. Similarly, if you try to remove something and there are no more elements in the sequence, oh wait, that's not true, so never mind. Right? Okay, so using an iterator is the only safe way to perform a filtering operation. Right? So suppose you want to remove all the negative values from a list. Right? You might write the following loop. Right? So here's our list. Right? I've put some numbers into the list. Right? So I've got some negative numbers, I've got some positive numbers. Right? Before today, you might, if I asked you write a loop that removes the negative values from the list, you might write the following loop. Right? So you write a little iterator-based loop. You write a little for each loop. So for each value in the list, right? You test, is the value negative? Right? And if it is, you remove the value. Right? And so if you try to run this code, it stops with an exception. And so it stops on line 16, which is the loop part here, which seems weird, right? It's dying somewhere in the loop, right? And if you look at the error messages, you'll see there's an exception, there's some method here that says check for co-modification, which seems weird, right? And so when you use a for each loop and you call remove using the list inside the loop, right? The iterator gets confused, right? So remember, the iterator knows how to look at the elements in the list, right? But if you change the list underneath the iterator, if you change the list, then the iterator is unable to deal with the change in the structure of the list, right? So if your removers add something to the list while you're iterating over it using a for each loop, it dies, right? The loop can cause an exception to occur. You might say, well, okay, I'm not going to use a for each loop. I'm going to use a counting style loop instead, right? You'll end up with a different problem if you use a counting style loop. If you use a counting style loop, you'll end up missing some of the elements to remove. You can try that on your own and see what happens there. Right? If you want to filter a list, then the correct way to do it is to use the iterator, because iterator has a remove method, right? And so if the iterator removes an element from the list, right, it knows how it changed the list, so it can handle the fact that the list is changed. right? And so the way you do this is you have to write an iterator-based loop that looks something like this, right? And so in the initialization part, oops, sorry. Right, you create a variable called iter, which is an iterator for the list. Right? How do you get the iterator? Well, you just ask the list for its iterator. Right? The condition for when the loop should run well, the loop should run as long as there's still some elements to look at in the list. Right? There's no update condition here when you write a iterator-based loop. Right? The update is going to be to call next, and we're going to do that inside the loop ourselves. Right? So the first thing you do inside the loop is call next. Right? So remember what next does, it gives you the current element that the iterator is looking at, right? And it will advance the iterator to the next element. Right? Now you can do your removal. Right? So if the value is less than 0, I can then ask the iterator to remove the value. Right? Remember what remove does, it removes the value that was most recently returned by the iterator. Right? So it removes the negative value. Okay, if I go out and comment out the remove method from here, the remove call to here, and the print here, and run this loop, right, you can see now that after the loop finishes running, all the negative elements have been removed from the loop. Right? So if you want to filter a list, that's the way you do it. Right? Am I going to ask you to filter a list on the exam? The answer is no. Right? So don't worry about committing that loop to memory. All right, so how exactly do you implement an iterator? And so to implement an iterator, you should understand, or you need to understand exactly what an iterator is. All right, so in your text editor, you've got a cursor, right? Typically, on most computers, it's a blinking cursor like this, right? So a cursor sits between letters, right? So that cursor here is sitting between the Y and the I, right? And so you can think of an iterator as sitting between elements. Right, so that red thing on the picture is my illustration of an iterator object. Right, so here my iterator is sitting between indexes 7 and 8. Right, so 7 I'm going to call, so the index 7 I'm going to call previous, and the index 8 I'm going to call next. Right, so when you call the next method, you get the element that's pointed at by next. Right, so you get the 6. And when you call next, the iterator advances to the next position in the list, right? So it moves over so that it's now between 8 and 9, right? So there's your iterator between indexes 7 and 8. You call next, it returns the 6, right? And advances one position to the right, right? Previous is now pointing at the, is now index 8, and next is now index 9. Right? So has next returns false when the iterator is at the end of the list. Right? So here's my iterator sitting at the end of the list. Right? So this is a list of 15 elements. Right? And so my array has a value null sitting here, which is our way of indicating that there's no element there. Right? So here my iterator is sitting between indexes 14 and 15. It's at the end of the list. Right? The next element, there's nothing there. So if you call next using the iterator, you'll get false. Sorry, has next using the iterator, you'll get false. If you call next with this particular iterator, you're supposed to get an exception. Right? There are no more elements in the list, so next can't return anything. Next can't return anything meaningful. Oops, sorry. And at the start of the list, so if the iterator sits between elements, then an iterator at the front of the list is sitting between no element, right? So there's no element before the first element, right? And it's sitting immediately before the first element, right? So in this case, next is going to be index 0, and previous will be index -1. And so using those set of pictures, we're going to implement our iterator. So our iterator is going to keep track of 2 indexes, right? It's going to keep track of next and previous, right? So next is the index of the element returned by the next call to next, right? Previous is the index of the element returned by the most recent call to next. Right? We're going to reset it to -1 if the element is deleted by a call to remove, right? And you'll see why in a minute. Notice here our array iterator class is not static, so that means it's an inner class. And remember that an inner class has access to the fields of the enclosing class. Right? So our array iterator class is defined inside of our sArrayList class. So it has access to the fields of our list. Right? It needs access to the fields of a list because it needs to get the element from the list. Right? So we need access to the array belonging to the list. So it has to be an inner class here. It can't be a static nested class. So those are our default, our no argument constructor. So this is the constructor that we're going to use when we create the iterator. Right? The iterator always starts at the front of the list. Right? So remember, at the front of the list, we decided that next should be 0 and previous should be -1. Right? That's the previous slide right here. Okay, how does hasNext work? So you just go back to the slide that describes hasNext. Right? HasNext will always return true unless you're at the end of the list. Right? How do you know you're at the end of the list? Right? Well, you know that you're at the end of the list if next is less than the size of the list, right? So here the size of our list is 15, right? We've got 15 elements in the list, right? As long as this dot next is less than 15, right, we can safely return, we know that there is an element in the list, right? If that's not the case, then we know that we're at the end of the list, right? So we need the size of the list. Remember, how do you get the size of the list from inside of a nested class, right? Use the name of the enclosing class, so sArrayList, then dot this, then dot size to get the field from the enclosing class. And then finally, how does next work? So just go back to the slide right here, right? So if we're sitting between, so remember previous and next, right? We're going to return the element sitting in this dot next, right? So we're going to return the 6 in this case, and then we have to advance the iterator 1 position. So ignore the statement up here, right? We want to get the element at this dot next, right? So if you want to, we can just ask the list for its next element by calling the lists method called get, right? Slightly more efficient is to just go into the array belonging to the list. Right? So I can access the array belonging to the list because this is a nested inner class. Right? So I can get to the array by writing sArrayList.this.arr. Right? I know the element that I want to get is at index this.next. Right? So I can do it that way as well. Right? This way is slightly more efficient because get always validates the index. Right? If you go directly into the array, there's no index. If you go directly into the array, there is no. Let me back up 1 second. So get, the method itself validates the index. When you go into the array, the index gets validated again because every time you access an array by index, there's a validation that happens. If you go into the array directly, you only pay for 1 validation. Right, so this is very slightly more efficient. Once you've gotten the element to return, you have to remember I need to advance the iterator to the next position. Right? And so that means updating the state of the iterator. So we have to update both previous and next. Right? So we're going to add 1 to next. Right? We're not going to add 1 to previous. Instead, we're going to write this previous equals this dot next. And why you have to do this will be clear in just a moment, I hope. Right? When you're done, you can return the element that you retrieved from the list back in this step up here. Next is supposed to throw an exception if there are no more elements in the list. How do you know if there's no more elements in the list? Just call hasNext. Right? So if hasNext returns false, we throw an exception. Right? And there's how you implement next for an array-based list. All right, so the reason why we're going to write this previous equals this next instead of this previous plus plus is because of remove. Right? All right, so I've got this iterator here. It's sitting between indexes 8 and 9. Right? What was the most recent value returned by that iterator? Right? So the most recent value that was returned was the thing sitting in index 8. Right? It was the 6. Right? the next element that should be returned by this iterator, right, is the element at index 10. Right? So we previously returned the 6. Right? The next thing we should return is the 10. Right? If you call remove, right, remove is supposed to remove the 6. Right? So we're supposed to remove that element there. Right? So I want to remove the element that's sitting in the index this.previous. Right? So what happens if you do that by calling remove? You get that. Right? So when I call remove, the 10 is going to come over one position, the 4 is going to come over one position, the 14 is going to come over one position, and so on and so on and so forth. Right? So they all move over one position, right? The 10 comes to here, the 4 goes to here, the 14 goes to here. Right? Our iterator hasn't moved, right? All that's happened is that we shuffled elements in the list over. So notice what's the problem, right? The problem is with this iterator, its next field points at the 9. So if you call next, it's going to return the 4, right? It's supposed to return the 10, so that's a problem, right? So next is now the wrong index, right? It should be the index of the element number 10, right? So that's easy to fix, right? If you call remove from the iterator, you have to decrease next by 1, right? So I need to move next over by 1, like that, right? Now, you could do the same thing with previous, right? So I could say previous is now the, move it over to the 7, right? But I don't want to do that, right? If I do that, I don't have any way to know that we've already called remove once for this iterator, right? And so remember what the requirements are of the iterator interface. It says of the iterator, yes, if you call remove, you can only call remove once for every call to next, right? So I need some way to indicate that I've called remove already. And so the easiest way to do that is simply to set previous to -1, right? And so if I set previous to -1, I can always look at the value of previous to determine whether or not we can safely call remove, right? And because I'm going to do this, right, so because I'm going to set previous to -1, I can't back here write this previous plus plus, right? If I do that, I'm going to get the wrong value for the previous if we remove something when we're iterating over the list, right? And so that line there is written the way it is because of the existence of remove. Right? Okay, so how does remove look like? So it turns out it's very simple, right? If previous is -1, then I know one of two things has happened, right? Either I haven't called next yet because the iterator is at the front of the list, right? So I'm not allowed to call remove, or I've already called remove once for the most recent call to next, right? So if this previous is -1, we simply throw an exception, right? Otherwise, what do we want to do? I want to remove the element at index this.previous. How do I remove that element? Well, we implemented remove for the list, so I'm just going to ask the list to remove that element for us. Right? And now I can adjust the state of my iterator. Right? Decrement next by 1, so that the next call to next returns the right value. Right? Set previous to -1, so that I know I've called remove once for the most recent call to next. And that's it. Right? And so the iterators are just a bunch of bookkeeping. So to implement one, it's not hard to do, but you have to be careful about the bookkeeping that you're doing. So that concludes our implementation of an array-based list. All right. Anybody have any questions about either the iterator or the array-based list itself? Yes.
Is this a first in, first out?
No. No, a list is a list, so you can do whatever you want with a list. You can add stuff to the end, you can add stuff to the front, right? You can take something away from the end, you can take something away from the front, right? So it's like a Python list.
But remove removes the most recently added element?
No, remove removes the most recent element returned by the iterator, right? So there's two remove methods, right, happening here. There's a remove method that belongs to the iterator, right? And there's a remove method that belongs to the list, right? If you're working with just the list, you can call remove on whatever element you want, right? You can remove whatever element by index in the list that you like, right? You can remove the first, you can remove the last, you can remove the middle. If you're iterating over the list and trying to remove stuff, right? That's when you're going to use this is the iterator's remove method, right? So there's two remove methods that are happening. Have you got it? Okay, so when you're talking about first in, first out, and last in, first out, you're talking about the collection itself, right? So in that case, you're talking about the list. So a list is neither of those, right? Similarly, the iterator is not a collection, right? So LIFO and FIFO, those concepts don't apply. Okay, any other questions? All right. So that wraps up our discussion of an array-based list. So implementing a full-blown array-based list on the exam is not a fair question, right? So it's beyond the scope of what you'd be asked for on the exam, right? However, would you be asked to implement an array-based collection of some kind? The answer is yes, that is a reasonable thing to ask you, right? The scope of the question has to be reasonable for an exam, right? Implementing the full list is not reasonable, right? Similarly, implementing the iterator for the exam is probably unreasonable as well. Right? And so I'm not going to ask you to implement an iterator either on the exam. You should understand what an iterator is, though, right, and what it can do. All right, so the last major topic in this course for this term anyway, is implementing a list using a sequence of nodes. Right? And so we're going to implement what's called a singly linked list. So a linked list is an implementation of a list that uses a sequence of linked nodes to represent the elements of the list. Right? There's many variations on this thing. So I'm only going to talk about the thing that's called a singly linked list. Right? So the node at the front of the list is traditionally called the head node. Right? And the node at the end of the list is traditionally called the tail. Right? You can also call it front and back, but by tradition they're called the head and tail. So in a singly linked list, each node has a link to the next node in the sequence. Right? There's a doubly linked list as well. So that in a doubly linked list, every node has a link to the next node and the previous node. So if you use Java's linked list implementation, you get a doubly linked list. Right? We're going to make a singly linked list instead. So a singly linked list looks basically the same as a linked stack or a linked queue, which we didn't talk about this year in this course. Right? So no queues in this course this year. Right? But that picture there, I mean, that just looks like a stack, a stack of elements 0, 1, 2, or zeros at the top of the stack. Right? Here I've got a list, right, where the first element in the list is a 0, the second element is a 1, and the third element is a 2. Right? So notice that the tail node, it has no node after it. So its next link is null. Just like the bottom node of a stack has a next link that is also null. Right? In the empty list, both the head and the tail are null. Right? There are no elements in the list. Just like in the empty stack. Right? That's the exact same picture for a stack. Right? And just like in a stack where you're implementing the stack using a linked sequence of nodes, right? Every node in the linked list can be thought of as being the head of some list. Right? So 0, 1, 2, the head of this list is the 0. Right? But if you go to the next node, right, then you can imagine that the 1 is the head of the list 1, 2, 3. Right? And the 2 is the head of the list 2, 3. Right? And the 3 is the head node of a list containing just the 3. Right? And so because the structure of a linked list is recursive, just like the structure of a linked sequence, just like the structure of our linked stack is recursive, right? Most of the linked list algorithms can be implemented recursively. Right? So if you wanted to, you could compute the size of a linked list recursively. Right? So our size method, you could implement in the following way. Right? So I'm going to call a recursive implementation of the size, passing in the head node of the list as the argument to the method. Right? And now our recursive implementation takes in some node. Right? If the node that comes in is null, we know that the size of that list, whose head node was that, is 0. Right? So remember, if the head node is null, you have an empty list. Right? So that's 0. So if the node is not null, then you know that that node that was passed in is the head node of some list. Right? So the size of that list is just 1, right, for the head node, plus the size of the rest of the list. Right? The size of the rest of the list you can compute recursively. Right? Call the method recursively, passing in the next node in the sequence. right? Because the next node in the sequence is the head node of the list missing the current head node, right? So there's your recursive implementation of size. All right, so our linked list class is going to be called S linked list, right? So it's going to implement the our simple list interface. It has the exact same node. Oh, sorry, it's the same generic node. So we haven't seen the generic node class yet. I'm going to show it to you in just a second, right? We didn't talk about linked queues in this course, so ignore that for a second, right? We did talk about linked stacks, right? The only difference now is that we're going to make the node class generic, right? So right here is our node class, right? So instead of being just plain old node, right, I'm implementing a generic list, so I probably need a generic node class as well, right? So our node class is now generic, right? The implementation, sorry, the code for this thing here, let me pull it up in Eclipse, is right there, right? So there's our node class, right? Inside each node is an element of type E, right? I guess more precisely, there's a reference to an element of type E, right? And then there's the next node following the node, right? And it's generic, so the node contains an element of type E, right? I've added a constructor here because it's handy to have a constructor, right? So we can initialize a node by passing in an element and the next node in the sequence, right? You can pass in null if you want there to be no next node, right? And that's it for our node class. So our list is going to keep track of a couple of things, right? So remember in a stack, we kept track of the top node, right? In a list, the top node is just the head node, right? The top node for a stack corresponds to the head node of a list, right? So there's head. In our stack implementation, we kept track of the size of the stack, number of elements in the stack, right? So we're also going to keep track of the number of elements in the list, right? I don't want to have to compute the size of the list every time someone calls size. And then finally, it turns out it's very useful if you keep track of where the last node in the list is, right? And so here, I'm going to keep track of the tail node as well, right? The last node of the, so that tail node, its next link will always be null. Okay. I've got a package private method here called head, and I've got a package private method here called tail. The reason these are packaged private is because normally in this course, if we get far enough in the course, we also talk about adding extra methods to the class. Sorry, not to the class. We talk about making a utility class that operates on linked lists, right? And so if you have a utility class that operates on linked lists, it needs access to the nodes of the list. Right? So if you put that class in the same package as your linked list class, right, it can call the methods head and tail, right? So that's the reason these exist. Okay, what does our constructor do? So the default constructor or the no argument constructor makes an empty list, right? So the size of an empty list is 0, right? There is no head node, there is no tail node, so those both get set to null, right? Size is easy, right? It's just like the size method in stack. We're keeping track of the size, so you can just return this dot size. Okay, oh, sorry, I called this NQ, that's a shame. So adding to the end of a list. So when we implemented a stack, every time you pushed an element onto the stack, we added a new node to the front of the list, right? When you want to add to the end of the list, it's a similar idea, right? So here, this says, look at the NQ operation for a queue. Unfortunately, we didn't talk about queues, so I'm going to show you a picture of this instead. Okay, so here's the general picture. Oh, wait, hang on just a second here. Adding to the tail. Okay, so if you're going to add to the end of an empty list, that turns out to be a special case, and so we'll deal with that in a second. Right. So adding to the end of a non-empty list, so all you have to do is you need to make a new node and stick it in here, right? So all that involves is modifying the tail node. So to add something to the end of the list, you just make a new node, right? So there's my new node n, right? I set the element in the node to whatever element we're going to add. So in this case, I'm adding a 3, right? Now what do? I need to hook that 3 up to the 2. Right? So I need to write tail next equals n, like that. Right? And that now joins our new node to the end of the list. Right? Finally, don't forget we're keeping track of the last node in the list, so we have to update tail so that it now refers to the newly added node. Right? That's actually not the last thing. You have to update the size as well. So the size now goes up by 4, up to 4, sorry. So there's your add method for a linked list. Okay, so if the size is 0, there is a special case, right? So remember, if the size of your list is 0 and you add something to the list, right? In an empty list, the head node is null, right? When you add something to an empty list, you now have a new head node. So you have to adjust this dot head as well, right? So most of the time when you're adding to a list, you're only adjusting the tail node. If the list is empty, you also have to adjust the head node. So if the list is empty, I have to adjust the head node so that it now, oops, sorry, hang on. I just lost marks for style. There we go. Okay, so when you add to a list, you just make a new node, right? And you store the element in the node, right? So I'm going to use my node constructor, store the element, right? And there is no next element to n. Right? In the special case, the list is empty, so I have to adjust the head node. Right? So the head node now also refers to n. Right? In all other cases, I just have to join the tail node to the new node n. Right? So to do the joining, it's just this tail next equals n. Right? Once you join the node to the list, update where the tail node is. Right? So the tail node is now the new node that we just added. And of course, don't forget to update the size, right? So the size of the list goes up by 1, right? And that's adding to the end of a linked sequence, right? If we had talked about queues, that would be adding to the end of a queue, right? So that would be the enqueue operation for a queue. Getting and setting by index. So the problem with a linked list is that many list operations operate by an index, right? Modify the element at index 5, right? And so the problem with a linked list is that you don't have a reference to that element, right? So doing anything by index requires starting at the head node, right? And then moving to the node whose index is the one you want to operate on, right? And so that is, so that's the weakness of a linked list, right? If you need to perform operations like get or set frequently, right, you probably want to avoid using a linked list. Right. All right, so any of these index-based methods need to move to the node at that index. So it's useful to write a method that can move to a node at a specified index. Right. Similarly, just like in in an array-based list, it's useful to write a method that can validate an index. Right. There's validate. It's the exact same thing. I don't remember what I called it for the array-based list. Right. It's the exact same method. Right. That index, it validates that index to make sure it's between 0 and size minus 1. Right. So if the index is less than 0 or if it's equal to the size of the list, throw an exception. Right. It's not a valid index for this list. Move to. Right. So to move to a node at a given index, right, it's relatively straightforward. Right. So there's a special case that's nice to take care of. You don't have to do this, but it's nice to do this. Right? So if the index is the last node of the list, right, then we already have a reference to that node. So I can just return this dot tail. Right? If the index is not the last node of the list, then I have to move starting from the head node. Right? So starting at the head node n, right, I'm just going to follow that many links to get to the node that I'm looking for. Right? So write a little loop. Right? I is 0, I is less than the index, I plus plus. Right? Advance n to the next node in the sequence. Right? So how do you advance n to the next node in the sequence? It's always n equals n dot next. Right? So that loop there simply follows that many links to get to the node that we're looking for, starting from the head node. Right? If if index is 0, the loop doesn't run, right? And n is the head node. Right? If index is 1, the loop runs once. Right? So starting at the head node, we go to the next node. So we're now at the second node in the list. right? If if index is 2, starting at the head node, we follow 2 links, right? And we get to the third node in the sequence, and so on and so on and so forth, right? Once we're done, we're at the node. Once the loop is done, we're at the node that we're looking for, so I can return n, right? And so notice the complexity of move to, right? That index can be up to the size of the list minus 1, so n minus 1, right? And so that loop there has complexity in big O of n, right? Every time you need to move to a node in the list, it has worst case complexity in big O of n. Right? You can also implement this recursively. Look at this slide if you have time and you're interested in recursion. Right? Okay, once you have moved to, get and set are easy to implement. Right? So the problem with move to is it's in ON, right? And that means your get and set are going to be in ON. Right? So get, validate the index, right? Move to the node at that index, return the element in that index, in the node at that index. Right? Remember that method right there has complexity big O of n. So get is also in big O of n. Right? Set is exactly the same thing. Right? Validate the index. Right? If the index is valid, move to the element at that index. Right? Set returns the element that was previously in the node. Right? So remember the element that was previously in the node. Right? Update the element now to the new element, and then return the element that was previously there. Okay. So so one of the places where a linked list performs faster than an array-based list is when you're doing stuff at the front of the list. Right? If I want to insert an element at the front of an array-based list, I have to move all the elements one position to the right. It's in ON. If I want to insert an element at the front of a linked list, I don't have to move anything. I make a new node and I hook it up to the front of the list. Right? So in a linked list, doing stuff at the front of the list is in O1, which is nice if you're trying to solve a problem that involves the front of the list. Right? So how do I add a new element to the front of an existing list? Right? So I'm going to make a new node that stores the new element. So I'm going to call that toAdd, so it's the one in blue. Right? So I want to make a new node that holds the new element, and I want to hook it up to the head node. Right? Once I've hooked it up to the head node, I now have a new head node in the list. Right? So I have to update the head node so that it now refers to the new node in the list. Right? So how do you implement add front? Make a new node. Right? Store the element in the node. Right? Your newly added node, you want to hook it up to the front of the list. Right? So toAdd next is equal to this.head. Right? So that joins the new node to the front of the existing list. Right? I now have a new head node, so update this.head so that it refers to toAdd. Right? And of course, don't forget the thing that's easy to forget. You just added an element to the front of the list, so increase the size of the list by 1. Right? Similarly to adding to the front, oh wait, this is inserting. Let me skip past this just a second here. Removing, here we go. Right? So similarly to adding an element at the front of the list, removing an element from the front of the list is also easy to do. Right? If I remove from the front of an array-based list, I have to move all the elements one position to the left. Right? To remove an element from the front of a linked list, I just remove the node. Right? So I just unhook the node from the rest of the list and I'm done. Right? So I'm going to remove that node sitting at the front of that list. So I'm going to call it toRemove. Right? I want to unhook this node, so I'm going to sever that link. Right? And when I sever that link, I want to make sure that I update the head node so that it points at the second node in the sequence. So before I sever the link, I'm going to get a reference to the node that has the 1. Right? So remove front. If the size of the list is 0, you can't remove an element from an empty list, so you're going to throw an exception. Right? I'm going to get a reference to the head node. Right? So toRemove is the current head node. Right? I need a reference to the next node in the sequence because that's going to be my new head node. Right? So this head is now toRemove.next. And now you have the annoying special case, right? So because we're keeping track of the tail node, right? If we remove an element from a list of size 1, right, the tail node now also gets updated, right? So if my list size is 1, I have to update the tail node because after removing the element from the list, there are no more elements in the list, right? So the tail node now becomes null, right? Then the size of the list goes down by 1, right? And then remove typically returns the element that was removed. So I'm going to return the element that was in the node to remove, right? And you can see here, if you look at this method, right, there are no operations here. All the operations are simple assignments and comparisons, right? And so that operation is in O1. Right? So the place where a linked list really shines over an array-based list is when you're doing something at the front or near the front of the list. Okay, so I think that's enough for this year. If you're looking at the slides, or if you're interested in how this thing works, you can see how, you can refer to the slides to see how you might add something to the middle of a list or remove something from the middle of a list. Right? And so the slides do go into some detail on how to do this, right? But you don't need to know how to do that for the purposes of the exam. Right? So for the purpose of the exam, it's sufficient if you study the stack, the linked stack implementation. Right? It's also good to know, right, what are the differences, what are the differences between a linked list and an array-based list, right? Why is inserting at the front of a list expensive for an array-based list, and why is it cheap for a linked list? Right? Stuff like that would be useful to know. All right, any questions about our list implementations? All right, so tomorrow morning, the plan is to return your second test and talk about the exam a little bit. There's already an announcement on OnQ that tells you what topics are on the exam and which topics are not. All right, so if there are no questions, I will see you again tomorrow morning.